Okay, in this section, we're going to investigate some non-ideal effects and changes to the ideal model that we've used to derive the behavior of the bipolar junction transistor. So the first one is base width modulation. So very similarly to the case in a MOSFET where the channel can change length, in a BJT, so we have our emitter, base, and collector. And if we start applying more and more base collector voltage to increase the collection, the width of the quasi-neutral region here in the base is going to get smaller and smaller. So this is with increasing V between the collector and the base. What this is going to do as that width gets smaller, remember our right-hand side here, in terms of the minority carrier distribution, represents one of our boundary conditions. So I'll draw these getting smaller and smaller here. And on this plot, I'm going to plot the minority carrier densities n as a function of x inside the base region. And so this means the slope of our carrier distribution is getting steeper and steeper and steeper as the base gets narrower. So as the slope gets steeper, our diffusion current, is going to increase. So we're going to get current, which is increasing, and it's a function of the biasing between the base and the collector. So let's look at what this does in terms of the current voltage curves. So we're going to plot the voltage between the collector and emitter and the collector current here. And I'll put the ideal curves as dashed lines. So ideally, this current should saturate. But really what happens is that the current increases linearly instead of saturating. And it turns out if we then project these lines back, they end up converging at a common voltage here. So this voltage is defined as positive, and it's called the early voltage, and that's E-A-R-L-Y after a person, not because it's turning on early. So this VA is somewhere in the range of hundreds of volts, and it's defined as a positive quantity. So if we think about what this means, it means that the slope out here, or the equivalent impedance of the transistor, has gone from something that should be infinite to something that's very large but finite. So the input impedance, we can say, is 1 over R naught, and that's equivalent to a conductance. And this is going to be IC over VA plus VCE here. And so the fact that this is a pretty large number acts to acts to make this resistance go down. I should say the fact that it's a finite valued number instead of VA being infinite, which would be the case if these were actually flat, is actually what decreases the input impedance. So that's our first effect, the base width modulation or early effect. So now let's look at our second type of effect, those having to do with high injection. So again, let's look at the carrier densities in our base region. And this base will assume to be P plus doped. So here I'll note the acceptor doping here. And I'll put way down here our minority carrier concentration in equilibrium. Now, because our emitter is over here and we're injecting electrons into this region, we develop this this slope to the NP of x. So this is what it looks like in low injection. And in high injection, what happens is this, this slope is going to increase in order to meet the much higher injected number of electrons at x equals 0. So this is NP of 0. But we've exceeded the number of equilibrium holes. Now this is a bad situation because what this would imply is that the base is actually charged negatively at that point. So it turns out that the base will actually bring in some holes to sort of counteract and neutralize that excess charge right there at the beginning. So this is P of 0, and this excess hole concentration is going to be drawn into the base. Now, what this means is that if we look on the other side, on the emitter side, the holes are a minority species on this side, and their equilibrium concentration might be down like this. So this means you're going to start back injecting some holes into the emitter as we increase this injected electron current higher than this doping in the base. And that's going to decrease our emitter injection efficiency, which, remember, is one of the factors that goes into determining our gains. So high injection is going to decrease our gain performance. So the net effect on the transistor performance, here's our gain, our current gain, and then the collector current here, and it'll rise at low currents, be flat for a while, and then once we hit this threshold for high injection, it'll start to roll off again. So you can push into high injection, sure, but you start to take a hit in terms of the gain. Now, high injection conditions also have another effect, and that's seen if we look at the collector current on a logarithmic scale as a function of the emitter collector voltage. So because of this effect where we're pulling in some excess holes at the same time to provide charge balance, very similarly to the diode in high injection, where we start to see a roll-off behavior for high injection currents. We see the same thing here, and the dependence is going to start to asymptote to x to the q times v over 2 kBt instead of the exp to the EV over kBt, which is followed at low injection. And this is sort of coming from the same effects that we saw in PN junction forward bias currents also. All right, so those are the main things to know about high injection in BJTs into the base. Okay, so the next effect comes from the fact that we want to very heavily dope the emitter in the first place. So remember that our structure might be like this. And when we dope so heavily, what actually happens is the band gap of the material decreases. If we plot the doping on this axis, as we get into higher and higher dopings, the band gap starts to decrease almost linearly with the logarithm of the doping concentration. And the change in band gap here is on the order of about 100 milli of electron volts. So silicon can go from having a band gap of 1.12 electron volts to something like 1.0. So why does this matter? It matters because the intrinsic carrier concentration, Ni squared, is going to be given by Nc Nv x to the E gap over kBt. So if we change the band gap even by a small amount, the intrinsic carrier concentration is going to go way up. That results in a decrease in the gain. So our gain coming from the component of the gain that comes from the emitter injection efficiency depends on some other factors out here, but right here appears the emitter's minority hole concentration. So if this starts increasing, that means that this increases for a given doping, and that means overall that our emitter injection efficiency goes down. And that means that you have to optimize the doping. You can't just dope as high as you can possibly. You have to optimize the doping in the design in order to maximize the overall gains. So our next effect has to do not with the band diagram so much of the BJT, but rather with its fabrication and implementation in common CMOS. So here's our emitter, base, and collector regions. And in some implementations, the collector is formed from the underlying wafer, but the base and emitter are formed by ion implantation into successively smaller wells. So what this means is that there's a lot of current trying to come in from the sides like this, and crowding up near the corners of the emitter structure. And this is conventional current. Of course, the electrons are going the other way. So the fact that the current density is non-uniform means that you can have localized heating in these regions. And so very careful two-dimensional analysis has to be made of the device operation in order to make sure that no damage or overheating occurs to the device structure. So again, this is mostly something having to do with the fact that we're implementing it in CMOS rather than the device physics itself. So the next effect we want to consider has to do with implementation again. And in this case, the implementation in terms of ion implantation actually gives us some benefit compared to the idealized structure with uniform doping everywhere. So non-uniform doping, how does that happen? So in a structure that's been ion implanted, the collector N doping is here. The base doping can be designed to have a fall off like so. And then the emitter can have a higher implanted dose, but a shallower range in the device. So this is our emitter N++, this is our base P+. So we've shown in a much earlier chapter that band bending and electric fields can actually be induced in the presence of non-uniform doping versus distance. And we'll use the result here that the electric field ends up being 1 over the local doping times the slope of the doping. So here we clearly have a dN by dx, and so we're going to have an electric field. So in the base region, so our regions of the device are going to be defined like so. And our P doping here is decreasing versus distance, and that means that the electric field will actually help electrons get swept through the base region. So the fact that in many cases these BJTs are constructed by ion implantation during CMOS compatible processing actually means that they can have a higher a base collection efficiency, and thus higher gain than they would if the layers were made uniformly doped. So this is actually a benefit rather than a non-ideality that we usually see, which degrades the performance. Okay, so our next topic is under the heading breakdown, and it's really two pieces. So the first one has to do also with what we talked about before, the base width modulation. And the idea is that if we increase the collector base voltage, reverse bias voltage, far enough, eventually the barrier will disappear and the entire base region will disappear. So just like in MOSFETs, this is called punch-through. And you can use the normal equations for depletion widths to figure out at what voltage in increasing reverse bias this will happen. Now, this other effects have to do with true avalanche breakdown. And in terms of the types of breakdown that can occur, we've already looked at carrier multiplication and breakdown in depletion widths. And at the base collector junction, the doping really isn't high enough to let Zener tunneling happen. So we're really talking about avalanche breakdown. And just remember that the emitter is usually operated in the forward active mode in forward bias, and therefore we don't worry about breakdown of this junction. There's some detailed analysis in textbooks about this, but we'll just mention that the fact that the transistor has gain makes the breakdown voltage for the structure in terms of the bias applied between the emitter and collector a little bit smaller than it would be otherwise. And it turns out that it goes as the nth root of the gain beta, where n is a constant between 3 and 6, having to do with the carrier multiplication process itself. So the result is that the BJT breakdown voltage is more, the BJT itself is more susceptible to breakdown than an isolated PN junction would be given the same dopings. And so when you're designing, you have to be aware of this factor, which reduces the breakdown voltage substantially, because remember this number is on the order of 100 or more. Okay, so that wraps up our treatment of the different non-idealities. Okay, so in this module about bipolar junction transistors, we started with an idealized model with uniform doping everywhere and derived the ideal behaviors with an analytical model. Now in this section today here, we've looked at some of the non-ideal effects and effects of real-world fabrication and the effects of non-uniform doping. So again, base width modulation and the early effect end up making the impedance of the transistor non-infinite and reducing the ideal performance. High injection conditions should generally be avoided because they end up degrading the performance of the BJT. The emitter gap narrowing also, if possible, should be minimized or reduced by optimizing rather than simply maximizing the doping in the emitter. And this actually has to do with another topic called heterojunction bipolar transistors, which we'll visit in the next section. So current crowding and non-uniform doping have to do with implementation, and one can cause damage to the device through overheating. So two-dimensional, three-dimensional design is definitely needed. And then the non-uniform doping that's imparted by ion implantation can actually bring benefits to the performance of the device compared to uniform doping. And lastly, we finished with a minor discussion of breakdown effects in the base collector junction and how that's modified by the gain of the transistor itself.